In this last part of our discussion of conditional probability, we're going to look at one example using conditional probability with some past data, and then talk about the probability of at least one. Babies born before 37 weeks are called preterm. The probability that a pregnancy results in a preterm birth is 11.7%. About 0.26% of all births resulted in a preterm baby who weighed 8.5 pounds or more. What is the probability that a randomly selected baby weighs 8.5 pounds or more given that the baby is preterm? Is this unusual? This last question about is this unusual starts to set us up for the purpose of probability inside statistics. But let's calculate this probability and then we'll break down that word unusual when it comes to probability. Given some information, probability that a pregnancy results in a preterm birth is 11.7%. And I'm going to change this to a decimal number, 0.117 divide by 100 percent per 100. The second statement, about 0.26% of all births resulted in a preterm baby who weighed 8.5 pounds or more. We're going to throw that or more in there. 8.5 is the minimum pounds for the baby in this discussion, and I forgot to type it in there. Notice that this percentage is referring to a preterm baby and 8.5 pounds or more. The question is asking us, what is the probability a randomly selected baby weighs 8.5 pounds or more given that the baby is preterm? So we're looking for the probability the baby is bigger than 8.5 pounds given that we have a preterm baby. So probability of a baby weighing greater than 8.5 pounds given that it was preterm. Well, since this is a given probability, we can set up our formula, probability of baby and preterm divided by preterm. And baby and preterm we got over here 0.26%, 0.0026, and then preterm 0.117. If we divide those out, let's do this division in our calculator. 0.0026 divided by 0.117. We get 0.02, repeating. 0.022 is sufficient. 3 decimal places. Now, this notion of, is this unusual? Unusual means rare or not likely to happen. Sometimes we say unlikely instead of unusual. And this really gets down to, is the probability really small? So unusual is really asking, is the probability close to 0? Now that idea of close can be arbitrary. So we have to be a little bit careful about this. Typically when we're talking about probabilities in general, we say a probability less than 0.05 or 5% is considered unusual. So if our probability is less than 0.05, we could call that probability unusual. In our example, 0.022 is less than 0.05, so we could say, yes, this is unusual or unlikely because the probability was less than 0.05. Later on, when we get into statistics, this idea of 0.05 being a threshold between usual values and unusual values in probability will not stay at 0.05. We'll look at what happens if we change that threshold to something different. If we make it smaller, like 0.01, or if we make it a little bit larger, like 0.1, we can make decisions based on this unlikelihood of something happening. But that conversation won't come back for us until chapter 7. So we've got a little ways to go before we talk about this idea of unlikely changing to something other than 0.05. So for the first 6 chapters, when we talk about unlikely events or unusual events, we're looking at events whose probability is less than 0.05. Now let's talk about the probability of at least 1. At least 1 means we're selecting 1 or 2 or 3 or all of something and calculating the probability. But notice the only number I left out was 0. None of something happening. So this notion of at least 1, if we're trying to find the probability of something, since I left out the 0, that's my complement. And instead of calculating the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability all the way up to whatever my total is, I can just calculate the probability of none and subtract that from 1. So let's see how we can put this into context. Here's an example. 35% of people who own cell phones use their phones to send and receive text messages. Though this is likely pretty old data, but we're going to roll with it. If we choose 4 cell phone owners at random, what is the probability that none use their phones for texting? And then the second part, the probability that at least 1 uses it for texting. So we can write down some information. Probability of using their phone for texting, 0.35. So that means the probability they don't use it for texting, 1 minus 0.35, which would be 0.65. Here we have another example of a complement. If we choose 4 cell phone owners at random, the probability none are using their phones for texting, we could set that up as the probability of 4 not texting, which means we've got the first one without text and the second one without text and the third one and the fourth one. Now, people generally are considered independent events when whether we select these people with replacement or without replacement, the population we're choosing from is very large. And there's a little blurb below this problem that I'll break down a little bit better. But assume with replacement, we've got independence. So that really means we can take that 0.65 for no text and multiply them together. So 0.65 for the first one, for the second one, for the third one, and for the fourth one gets us 0.65 to the fourth. And if I'm doing that on my calculator, just to show you what it looks like, I'll clear my entry. 0.65, here I'm using a Windows calculator. I'm looking for this x to the power y button. So this x to the y button, you see in my display up here, I've got this little caret indicating an exponent, and I'll do it to the 4th power. 0.65 to the 4th is 0.1785. 1785, which the 5 would cause me to round it up to 179. So the probability that none of the 4 people selected use their phones for texting is 0.179. Now what's the probability at least 1 uses it for texting? We could look at least 1 out of the 4. Using our definition of at least 1, or this idea of complements, we could look at 1 minus the probability of none. The probability of none for the 4, we just calculated it, 0.179. And so we get 0.821 for the probability of at least 1. So we want to use this idea of at least 1 if we already know, or if it's easy to calculate the probability of none. we can use this complement and find the solution. Now, to do it the long way takes a lot more calculations and a little bit more technique than we've learned so far. So we'll have to wait on that a little bit later. But I wouldn't recommend it. Calculating lots of different cases together, and the calculations get messy, especially working with these decimal numbers. But let's take a look at small samples from large populations. If we're taking a collection of people or items from a large population, so if a sample size that I select is no more than 5% the size of the population, we can treat the selections as being independent, even if the selections are made without replacement. Consider a very large jar of tokens. Let's suppose the tokens are numbered in such a way that they're all different, and there are thousands of them. You can even just say 1,000. If I select 3 of the tokens from the jar, then for each token that I pull out, when I pull out the first one, and then I pull out the second one, and I pull out the third one, removing the first token out of 1,000 different tokens does not change the probability of the third token being drawn enough to make a difference. So we say that we can treat these selections, even though they're without replacement, we can treat them as independent to make our calculations a little bit easier. And this is typically what pollsters use to come up with results. A Gallup poll reported that 52% of Americans used a seatbelt the last time they got into a car. If 4 people are selected at random, find the probability that they all used a seatbelt the last time they got into a car. And we're talking about Americans, which are 40 million people, and we're selecting 4 people at random. So we're definitely not changing that probability enough when we select these 4 people. So we're going to assume independence based on this idea from above, small samples from large populations. And so we can calculate the probability 4 used a seatbelt as being the first one using a seatbelt times the second one using a seatbelt times the third one using a seatbelt times the fourth one using a seatbelt. 0.52 to the 4th power, simplifying it just a little bit. And doing that just one more time on our calculator so that we know how to do it. 0.52 x to the y 4. And we get 0.0731, 0.073. Now when you're looking at your scientific calculator, whether it's on your phone, on your computer, or an actual calculator, you will have an exponent button. That's one of the required buttons of a scientific calculator. So see if you can find it. If you can't find your exponent button, you can always send me an image and I can find it for you. So send me an image of your calculator and I'll help you locate it. And there we have the probability that all 4 used a seatbelt they got into a car is 0.073. Now, the last question. Is this considered unusual? Is this an unusual probability? 0.07. We talked in the last problem that unusual means smaller than 0.05 for us right now. So since this probability, 0.073, is greater than 0.05, we would say not unusual, or not unlikely, or just likely, to eliminate the double negatives. This is still considered a small probability, 0.07, 7 out of 100. But for us right now, 5 out of 100 is going to be called unusual.